just start then. Hello everyone, thank you for coming. Today Tianhua will be presenting his research on tall walls with minimum longitudinal reinforcement limits. So Tianhua is a PhD student with Rick, and today for the first time another lecturer is here for the meeting, which is good. And I'll leave it to Tianhua now.
I'm just going to see what you've been doing.
Thanks, Rick, for coming for support, and thank you everyone for coming to the presentation. Thank you, thanks Max and Pavan for organizing the forum to provide opportunity for sharing the OpenSees technique. So today I will talk about my research project on seismic performance of tall wall design with the minimum longitudinal reinforcement. Show slide. Design with the minimal longitudinal reinforcement limits. So in recent decades, the increase of urbanizations accelerate the tendency in construction of tall, high-rise buildings. Here rise the questions: does the tall wall perform the expected response as we design assumptions? My research project is trying to answer these questions. So my presentation will involve two parts. The first part will talk about the research project, which involve in the research program and the parametric studies. The second part will talk about the OpenSees modeling technique, which will compare the connect scheme in OpenSees. So let's have a look at research background. The damage wall observation in the Christchurch earthquake find the reinforced bar ruptured at the plastic hinge for the lightly reinforcement wall. And based on the past research, both American and New Zealand standards increased the requirement for the reinforcement amount in the plastic hinge. Compared with New Zealand standards, the American standards require higher additional reinforcement terminational height. But New Zealand standards have the advantage in capacity design. This means oh, thank you. This means the additional reinforcement in wall design should not only satisfy the minimum requirements, height requirements, but also it should satisfy that the additional reinforcements should stop where the section capacity was greater than the section demand. For tall wall design philosophy, we want the large inelastic deformation will concentrate at the base plastic hinge regions because that was ductile design. We never expect the failure will occur outside plastic hinge because that place was limited or non-ductile design. The past earthquake gave us the lesson that the insufficient reinforcement outside plastic hinge will cause the building flexure at middle height. So does the wall design based on the current standard requirements can provide the sufficient safety? In order to answer the questions, the parameter study on a 20-story prototype wall will conduct. The tall wall section was designed according to the latest American standards. That the additional reinforcement was lumped at the boundary at the sections, and the dispute reinforcement were assigned at the web sections for the wall in plastic hinge. For the wall outside plastic hinge, there are no lumped additional reinforcement, and all the distribute longitudinal reinforcement were assigned along the sections. For each story wall, four equal lengths of displaced-based element was used to model the flexural response, and the zero length was merged into 1/4 and 3/4 of the height of wall to simulate the shear response. So the parametric study will investigate four key parts. They are actual load pattern, reinforcement amount effect, and reinforcement property effect, and the geometric effect. So let's have a look on the effect of actual load pattern. The modeling wall was investigated from 0% to 12% of base actual load ratio. And we can see from the moment profile that the red line respond the section capacity, and the blue line showed the ultimate moment demand. From these four figures, we can know that the wall designed with American standards satisfied the capacity design that the moment capacity at terminational height was greater than the moment demand. Does that mean the wall will perform the expected response as the standard assumptions? The answer is probably not. Except the wall without actual load, the other three walls showed the reinforcement yielding will over the base plastic hinge. That means this was not correspond with our assumption that the wall will perform the perfect elastic behavior outside plastic hinge. So here we have two questions. The first one may be, how can we define the appropriate reinforcement strings at the terminational height? The second one is, how can we control the string at terminational height? The first question maybe we can discuss in later, but the second question, the answer may be increase the reinforcement amount. So the primary approach is to increase the additional reinforcement height. Therefore, a group of models with different additional reinforcement height from 2-story to 7-story was conduct two analysis. As we can see from the figures, except 2- and 3-story additional reinforcement, others wall showed the moment capacity was greater than demand. But how is wall performance for the less capacity wall in 2 or 3 additional reinforcement? The answer is the reinforced bar will fracture at the terminational height rather than fracture at the base plastic hinge. This was the unexpected failure that we never want to happen. And we can also, from the other 3 figures, that the reinforcement strength was reduced with the increase of additional reinforcement height. But even for 7-story additional reinforcement height, the strain were still over yielding at terminational place. Some people will say, for tall wall design, maybe we should concern about the plastic hinge design, because the more reinforcement amount in plastic hinge will cause the large capacity of the wall. Maybe it will reduce, resulting the large deformation capacity. Is that correct? Probably half-half. As we can see, the moment profile or moment drift response, the blue line showed the wall with double reinforcement at the plastic hinge. It shows the larger strength capacity, but the lower drift capacity. Why? The answer is the overstrength for the plastic hinge range will cause the weak portion fall outside the plastic hinge. This will resulting the reinforced bar will fracture outside the plastic hinge. That was an unexpected failure we want to have. So some people may say, yeah, maybe we can amplify the reinforcement outside plastic hinge, and that will benefit for reduce the strength at terminational height. Is that correct? Probably. As we can see from the moment diaphragm, for double of reinforcement outside plastic hinge, the wall sections was larger than the section capacity over the plastic hinge was larger than the section capacity in plastic hinge. That will never happen in practical engineering. But let's see what will happen. The strength file perform a very beautiful and smoothly strength file. Compared with other wall model that has a sudden increase at terminational height. But although the profile was very beautiful, but it's still over yielding at terminational height. So the previous model was used the reinforcement bar designed according to American standards. How is the for the American standards, the reinforced bar, the ultimate for the reinforcement bar, the ultimate to yielding ratio was 1.47. But for New Zealand standards, the ultimate to yielding ratio was around 1.2 to 1.25. Does this also influence the strength at terminational height? So 3 groups of different ultimate to yielding ratio was used to investigate from 1.0 to 1.45. The 1.0 represents the material, the perfect plastic material property. As we can see that with the reduce of ultimate to Yangling ratios, the strength was reduced at the terminational height. Yeah, we can see here, here, here. Yeah, it's reduced. So now let's talk about the geometric effect. In order to make the presentation simply, please let me just show the conclusion in advance that the geometric effect is not a sensitive parameter. And I investigate the height of wall from 8, 10, 15 with 3, 4, 5 story of additional reinforcement height. The moment draft response showed the same, and there's nothing special for the moment diaphragm. Also, there's nothing special for the strength profile. Then I investigate the wall length effect. That the shorter wall will cause the large draft. This was because for the constant reinforcement strength, the short wall will cause the large sectional rotations that will cause the large draft for the wall. And the moment profile and the strength profile was nothing special. And also I investigate wall thickness effect from 200 to 400 millimeters. As we expectations, the thicker wall will perform the higher strength capacity, but the draft capacity was the same. Nothing special in moment profile, nothing special for strength profile. So here we can have a short conclusion that the parameter, the sensitive parameter for tall wall design is the axial load pattern, the additional reinforcement height, reinforcement amount, and the reinforcement properties. And the geometric effect is the non-sensitive parameter. So here, let me answer the questions. What is the appropriate strength at terminational height? The latest tall wall design standards for Los Angeles regions, which posted in this year, recommended the strength over the plastic hinge should come true within 2 times of Yangling strength. This means it will be around 0.4%. In order to find the relation between the strength and the additional reinforcement height, the fitting functions was used to find the appropriate additional reinforcement height. That for the 8-story additional reinforcement wall, the string at the terminal height will satisfy the design assumptions. This means both New Zealand standard and the American standards can not satisfy these assumptions. All these models are based on the monotonic pushover analysis, and the time history analysis will conduct to investigate the high mode effect for the tall wall design with the lightly reinforcement account. So another interesting I want to show is I also compare with the international standards. that the American standards highlight the additional reinforcement height, and the New Zealand standard highlight the up reinforcement ratio, and Chinese standard highlight lower reinforcement ratio. For both American and the New Zealand standards that satisfy the capacity design, but Chinese standard not satisfied capacity design. And the wall will flexure outside plastic hinge. That was terrible. So let's have a talk of the OpenSees modeling technique, because the regularization issues and the concrete softening behavior was discussed in the previous quicker monthly meetings, and I don't want to make audience feel boring. So today's presentation, I will show some fresh issues on connections scheme, because my research will also focus on the core wall system response. So the non-rectangular wall modeling is another challenge.
Just a clarification, are you using this model for the analysis results issue?
Yeah, yeah.
Separate?
Yeah, this model I showed in the last quick presentation.
No, I'm asking, the results you presented,
yeah,
are from this model?
No. It's from the rectangular wall model I showed.
Okay.
Yeah, beginning. This was separate part. The C-shaped wall, I have showed the C-shaped wall in last quick presentations that I modeled the C-shaped wall with 3 individual segments that was connected with the rigid bars, and the result was shown on the left. It's not perfect, but it was acceptable. Then I extend this model scheme to the core wall modeling, and find that the strain profile for the web direction and the flat direction was not constant at the corner. How to solve this problem? I replaced the rigid beam to rigid bar for modeling, but it will cause the convergency issues. And I think maybe the elastic material can solve the problems. And so I add one more node at the corner between the section between the flash and the web regions. But the result was not stable. And I think maybe I can use 2 nodes at the corner, and use equal degree of freedom to connect with 2 nodes. But the result was boom. So I think maybe I should change the nodes assignment, that I can keep the 3 nodes as a line and connect with the 3 nodes, use elastic material. But to my surprise, that the material definition for 3E6 MPa and 3E7 MPa is okay, but 3E8 MPa was show different results. Maybe it was quite sensitive for definition the elastic modules. So I think maybe I can use the same scheme, but use the rigid bar and the rigid beam or rigid diaphragm to see what happens. For the rigid beam, rigid diaphragm, the result was not good, but okay. But when we look at the local behavior, we can find that the deformation was not compatible at the corner for the elastic material. Also, for the rigid diaphragm, the strain profile was not compatible. The deformation was incompatibility at the corner region. In order to solve these questions, the fiber model has advantage for model the non-rectangular sections. So I set the nodes at the centroid of the C-shaped wall, and the result was showing left side. It seems much better than previous model. And also, I extend this scheme to the core wall modeling. The strain profile was compatibility at the corner. So let me have a short summary. All connection scheme discussed above, including the elastic beam, elastic bar, and the elastic diaphragm, cannot provide the deformation compatibility at the corner regions. The entire non-rectangular wall sections model can issue the deformation compatibility in the core region, but it cannot consider for the shear lag effect. Maybe it's time for lunch. I hope my presentation will not spoil your appetite. So thank you. That's all.
Thank you, Tianhua. We can ask questions now.
Yes, please.
From the previous year results, you had said that for short walls had larger drips.
Tall wall was very lightly reinforcement amount, low reinforcement amount. Yeah.
You had said something about the short wall having larger drips.
The short wall may be control, the squat wall may be control for the shear response. That was different model schemes with the large tall wall, because the tall wall was controlled by the flexural response, and the shear response was only count for a small amount of for total deformations. So this was different model scheme. Thank you. Any questions?
Yeah. Under geometric variations, you had said that results are almost insensitive to variations. So a thicker wall, you say almost the same strains as a non-thicker wall.
Yeah.
So the thickness would mean that it is more simple. So the drift and the response would be a bit different.
Yes, because the for the wall with geometric effect investigations, I impose 0% of actual load patterns, so it was quite safe. But if we impose the higher actual load, it will cause the yadding over the plastic hinge.
To continue that, like you said, the geometry has no effect.
Yeah.
So what about the slenderness ratio, or like the effective height of the wall?
Yeah, it's what.
It will affect, right? So you said like there is no effect of geometry. I didn't understand that one.
Oh, because we can let's return back to the wall height geometry. That I investigate 4 types of wall, including 20-story with 5-story additional reinforcement height, 8-story with 3 additional reinforcement height, and 10-story with 3 additional reinforcement height, 15-story with 4 additional height.
But all your wall lengths are same, 8.5.
Yeah. All the walls are the same. I just investigate the height.
What is the wall height effect? That's what I didn't understand.
high mode.
If the length of the wall is same, how are you varying the height?
Horizontal length, not height. The height is your number of stories, right?
Yes,
The length is the length of the wall section.
yes, the length was the wall section.
That's constant. Just increasing the height.
Oh, so each wall is like 8.2 and 28.2 meters.
No, 8.2 is the long dimension of the section.
Oh,
Yeah.
okay, on the plan.
Yeah,
Okay.
yeah, on the plan. Yeah,
Oh.
thank you.
But like the height of the wall has no effect on the result.
The height of wall not affect on the result. Yeah,
So if you're saying
the additional
10
reinforcement.
meters or 100 meters doesn't affect.
It will affect in dynamic response because the higher wall will show in the higher mode effect. So for the static pushover analysis, there are not large difference, but for the earthquake or for the time story analysis, it will have the difference. That will be conducted in the next part.
And is that because you have not assumed the actual loads?
I assume the first part I investigate different actual loads from 0% to 12% put load at the top of the wall. Yeah.
And what is additional reinforcement mean? What is that?
Yeah. Additional reinforcement means is that for tall walls we put more reinforcement at the base. At the plastic hinge range, we put more reinforcement height at the plastic
For the lower
range.
stories.
Yeah, for low stories. Yeah.
But that's the part of the design reinforcement only, right? It's not like, is it given in addition to the design reinforcement or is it like part of the design reinforcement?
Additional to what's the standard and then what you're adding on.
Why is it named additional reinforcement? That I didn't understand. Like if it's
Additional reinforcement means we should put lump additional reinforcement in the boundary elements. Okay. So the standards require the minimal height for stop the additional reinforcement. But my research was on whether the required height was enough to make the wall perform the aspect response as assumption.
You call it additional because it's the minimum reinforcement requirement.
okay.
So it's an additional requirement.
Okay.
Okay. Not additional to.
We are not providing
more strength required.
It's still based on the code. Okay. And you said base axial ratio. What does that mean?
Base axial ratio is base S.
Is it different from axial load ratio?
Yeah, because I impose the gravity wall to each story. So for the base axial ratio, it was 4%, 8%, and 12%. Because I dispute.
So how is it different from the regular axial load ratio? Is it any different or is it the same?
It's the same.
Okay.
Yeah.
Question.
Yeah.
When you did one model type,
yeah,
the diaphragm,
yeah,
what was the thinking process like? Why did you add a diaphragm? What the thinking process? What were you expecting to happen when you added a diaphragm? You mean
for the connection?
Yeah. So what was the thinking process like? Why did you add a diaphragm?
Okay.
It's not there, right? So
yeah, it's not right.
What was the thinking process?
I think the diaphragm we assume. For the rigid bar assumptions, it only can transfers the force, but not rotation, the moment rotation. For diaphragm, it's make the whole wall sections will rotation as the plane remain plane assumptions. So yeah.
And then the solution when you add the centroid, what's the difference? Like the best model that you think?
This model, this figure?
The final one, which is you think is the best model?
Oh,
You had,
the solution is I use one node to model the whole wall sections. Use one node. The previous model I used three nodes, and the node was set at the center of each section center, or set 3 nodes as a line.
So how are you joining the? So you said you are using a fiber section here.
Yes,
right?
yes.
So and you have an element connecting 2 nodes?
No, only one node. So I do not need any connections.
So
Avoid the connection.
In vertical.
Vertical, just use the display space element.
Yes. So the fiber section is, so how many integration points did you use, like 2 or 3?
I used the display space element, and I used 4 equivalence display space element, and emerge as the tall wall modeling. I emerged the shear spring at 1/5 and 3/5 of the height.
What did you invert? Sorry.
I used display space element and emerge the shear spring at 1/4, and 3/4 of the wall height.
What is that doing?
Because we know for tall wall it's controlled by the flexural response, but there still has some shear response. But for the fiber model, it's only considered for the flexural and axial response. So in order to consider shear response, we need to add additional shear spring.
Why can't you add, like using an aggregator, you can add like the shear also, right?
Yeah,
fiber section.
Yeah, but
Why do you need to use a spring externally?
It works for the force based element, but it doesn't work for.
No, for displacement based also.
No.
It definitely works. I used it, so.
Maybe you can try. Maybe you can show me the result. Yeah.
Because it's just using an aggregator, you can just use like for torsion or for shear over the fiber section. So.
Okay. From my note, I think the integration shear section maybe work for the force-based element, but the shear springs, additional shear spring was work for the display-based element. Maybe we can discuss later. Yeah.
So you said this shear spring is located at 1/4 of the wall.
Yeah.
What's the basis of that? Like, why didn't you put that?
Because from the past research in 1978, yes. The professor of Stanford maybe proposed that we should divide the wall in 1/5 and 1/5 of equal degree of freedom, and set some shear springs, and during 206, and Bear in Switzerland investigates two shear node springs along the wall, and investigate with her experimental model and find this scheme is acceptable. So I use his model scheme.
Okay. And one more thing is like where you were checking the reinforcement, like the amount of reinforcement.
Yeah.
Can you go to those plots? You said when you double the reinforcement. Yeah, go back. Sorry. Yeah. You increase the reinforcement twice, but the stiffness of the wall did not change when you elastic stiffness.
Because the stiffness was the same before the reinforcement cracking.
So you are saying like section capacity did not increase?
The section capacity was increased. We can see the blue line showed the larger strength capacities than the red line. The red line was the initial model.
So what I'm asking is, up to 30,000 kilonewton meter, the concrete must have cracked by then, right?
Yes, must crack. Yeah.
So what I'm asking is, if you have twice the reinforcement, like there should be at least not exactly double, but like some increase in the stiffness, right? They're almost same.
Yeah, that's true. The reason why we do not have see as significant strength drop is because we have the wall was modeled with the actual load. The actual load will prevent the wall cracking, will prevent the sudden stress loss. And we, as for the stiffness issues you ask, the the wall with double stiffness or with double reinforcement still show the larger stiffness. We can see the stiffness for the for the blue line was larger after 30,000 Newton.
And one more thing is, you said like you have regularized reinforcement and standard reinforcement. What is the difference?
Sorry.
Regularized reinforcement and standard reinforcement. What is the difference? Like
regularized them
in reinforcement, one of the plots you compared regularized and standard.
Oh, which is this figure? Is this figure? The figure compare with
no, before I think. There are no numbers.
I think it was the one with the green line and the blue line, where you have a standard and the regularized. I think so.
Yeah. So I just wanted to ask how he did that.
Which slide?
Yeah.
Yeah. Oh, okay.
So how did regularized model? How did you get that?
Oh, I regularized the model according to Pew. Yeah.
So can you explain more, because I think that will be useful for people. How you did the regularization stuff.
Okay. Because the fiber model was based depends on the mesh size effect. So mesh size effect. So it depends on the calculation length or element length. So in order to set was based on the constant energy release. So in order to achieve the same energy release, we should regularize the material. So my model was regularize the green line is the standard material property, and the blue line is the model material property.
I mean, is it like a standard process everyone knows? Like, I'm just asking because other users might not know it, and for them it might be useful if you can explain the process of how you did the regularization, not what is regularization. How you did that? How did you incorporate it?
I follow issues recommendations. Use the same energy release.
Okay, so it's like a standard.
It's that.
You need to maintain this same fracture energy. All that.
I mean, I know it, but like a lot of people might not know it, so that's why.
I understand. Did you regularize the steel, the reinforcement?
Yeah.
The reinforcement. So what did you change in which steel model did you use?
Steel O2, yeah.
And what did you play with to reach the same energy?
It played the same energy.
Strain values, or like did you play with like
strain, ultimate
strain value?
Yeah, peak strain value.
Yeah, that's what I was like.
Yeah.
Okay.
Cool. Yeah, that's how you usually do. Like you play with the peak strain values.
So what I know about regularization, you do it with concrete and play with the ultimate at the bottom. But with steel, I do not quite remember.
I know
what are the parameters that you change. But cool.
And
thank you.
In some of your plots, when you're plotting the moment drift and wall length effects, you have a lot of bumps in the model results. And why did you get those things? Because those are important stuff.
This one?
No, not here. When you're plotting moment and moment versus drift in wall length effects. Wall length effects.
wall length effects. Wall length effect. So
Yeah, here.
oh,
Why do
okay.
you have
Okay,
all
okay,
those?
okay. Okay.
Why is it not?
Okay.
Is
It is very quite interesting things. Yeah. Thank you for your mentions.
Yeah.
Because the walls show the center not smoothly curved because each curve presents a cracking will happen at the wall along the wall height. This will cause the unsmooth because this wall was modeled without any extra load. Compared with others with smoothly moment profile, the wall was modeled without extra load. So it was very easy to subject the cracking.
So whenever it's cracking at a particular level,
yeah,
losing the stiffness and it's going back again.
Yeah. You can see it's sure a certain crack, and then the strength will make up by the reinforcement. So the strength will.
So it's not nothing to do with the rebar breaking or something like that.
No rebar. Rebar breaking means the strength will drop dramatically and won't be returned back.
Like in the last, right?
Last
in
rate.
the end.
Yeah.
Yeah, because it was interesting to see that because you have a last sudden drop and you have intermediate drops.
Yeah.
It's important to know what's coming from there.
Yeah.
Might be a naive question, but how did you validate that those drops are cracked in the concrete and are not numerical instabilities?
Also, good questions. I can show some. I can show some. I have validated with the I'm not sure whether I have the.
You could just like how did you know it's not numerical?
I have validated with the lighter reinforcement test, and this shows.
So you compared it with experimental results.
Yeah. I think it cannot find here, but if you're interested, I can show you later. Yeah.
So when you compared it with the experimental results, the experiments also have those kind of.
Yeah.
It's the same locations, but like they also have stuff.
Yeah.
Okay.
Yeah, I compare with the previous H model. It was tested very light reinforcement of 0.15% of reinforcement. Yeah.
Anyone has any other questions? Then you have one. Okay.
Yeah.
And one more thing I noticed was like in your models. Can you go to your modeling fiber section?
Modeling.
OpenSees modeling stuff.
Or OpenSees modeling stuff.
Yeah. And where you were, somewhere. Can you go down? Next one, please. Yeah, here. Can you make it big?
Make it.
So one interesting thing I noticed was on the positive cycle, it was matching well. On the negative cycle, it's like not reaching full capacity consistently. Why was that?
Yeah, it's a good question because the negative portion is for the wall with let me is this for the flash directions.
But you're not
in the test, it was buckling. So my model was not considered about buckling.
No, when you are modeling, for example, the rigid beam, you just model the three nodes. The rigid beam. The middle one.
The middle one. Okay.
This one. You just model the 2 elements and 3 nodes, right? And you didn't do anything for the
three elements. Two flat sections and one web directions, and I set nodes as the one line.
So my question is, did you model the like the flanges coming out on the top and bottom?
Yeah, at the top and the bottom.
Here in this model?
Yeah.
How did you model them? Like using another?
No, I just sent since the center of the section was on the right of the sections.
Oh.
Yeah.
So that was not clear. Okay.
Yeah.
So
I not set the nodes of the section at the central. I moved the place.
So pretty much you moved the whole section and made it like an I section. Then.
Yeah.
It's not like a C section then.
Yes, this is why I set it the center rate in the next model scheme. I set it the center rate of C# was center rate.
But still, like the response on the left side is not same as like the response on the Y side.
Yeah.
Do you know why?
Because I think the main problem is probably is the deformation compatibility or compatibility problems, because it is hard to perfect make the three section move as the same sections. So that's the reason. And we can also find it was not deformation compatibility at the corner regions. This is the problem.
May I ask one question?
Oh,
yeah,
sorry.
yes,
That's good. Like
yeah.
I forgot about the people online.
Yeah.
Okay, thank you so much for your very nice and detailed presentation. May I know, did you consider the bond slip restraint between the concrete and reinforcement?
Yeah. For the tall wall simulation, I do not consider about bounce slip, because for the total deformation for tall wall, bounce slip only count very small percentage. But I also model some the core wall system, and I for the complete modeling, I model with the boundary slip with the long plastic joint at the end of the beam.
Mm. And what kind of constraint did you use? I mean, regarding the code, what kind of constraint was it? Like equal DOF or some rigid beam equal DOF?
For the core wall modeling, nowadays I set for the core wall pier, I use the single nodes for each wall pier, and as we can see the left side, for the wall and beam connection, I use a rigid arm to connect wall connect wall and the beam nodes. And also at the same place, I apply additional nodes. This was used to present as discussed before. I use this node to present the shear spring and the moment rotation spring. So
yeah, but this is I think what I understood, it's I think not related to the reinforcement and concrete restraint. I'm talking about the concrete and reinforcement. Did you consider the restraint between concrete and reinforcement, or you just model concrete and consider as a confinement and unconfinement phenomena?
oh yeah. I have considered about confined
In order, I mean, in order to take into account the bond slip phenomena. Because if you consider the bond slip phenomena, you have to restrain and you have to assign either equal DOF or rigid beam plus equal DOF, some kind of constraint.
Shall I ask him what sorry, Nisar, like what you're mentioning is like in the fiber section or within the fibers? Okay.
Within the fibers, actually, I'm not sure about OpenSees code, but for example,
so the
if
fiber sections
yeah,
assume perfect bond between the concrete and reinforcement.
Exactly. You are 100% right. For example, if you consider the fiber section,
yes,
you may in that section we only use the we only consider the confinement and unconfinement
yes,
phenomena.
using Mander's model or whatever. Yes,
exactly.
Yes.
So when, for example, when we have the possibility of bond slip failure mechanism,
Yes.
then we have to assign constraint between concrete and reinforcement.
So
for
there
example,
are other ways
yeah.
to do that, but what Tianhua was telling is like he did not consider the bond slip effects because like for tall walls, apparently they are negligible. So the drift coming because of the bond slip is very less, the contribution of that.
Yeah.
So that's why he's kind of ignoring that here.
But don't you think during seismic loading it would be,
so
because
he's
it's
just doing pushover analysis or cyclic pushover. At this point, he's not doing for seismic yet. Are you going to consider that?
Yeah, I will doing the dynamic analysis for investigate the high mode effect for tall wall. Yeah, but yeah.
I mean, that's a very good point you're asking, but like at this point, it was not.
Yeah, because it needs a very detailed modeling, and it's very complicated to assign, and still I think it's not yet completely available in OpenSees library.
Actually, it is not. You're correct about it. If you want to use like the bond slip models and stuff, like presently, because I am also kind of trying to do similar stuff. If you want to use a fiber section, then it's what you have to do is you have to put the reinforcement and then like the concrete, and then you have to use friction elements to do a very complex model. I still don't know how to do that, but like there are other ways you can replicate the bond slip model, but yeah, in fiber section it's very hard to do that.
Yeah. Anyway, thank you so much for your very nice contribution, and you are doing a great job discussing this forum. It's I mean, it's a good platform. You guys are doing very well job. I'm from Italy, and it's almost 12 a.m. in the night. So, but I'm enjoying too much.
Thank you for your.
Thank you for joining.
For joining.
No, welcome.
Thank you.
So, do you have any other questions?
No, thank you. That was my concern, and maybe next meeting we will have some useful more. Maybe I will contribute myself as well. I will show you some more.
You can send me an email about your stuff, and we can. I mean, we are more than happy to have you and present you here.
Yeah, thank you so much. Thank you so much.
Yeah.
Thank you. Oh, thank you for interesting.
Cool. Any other questions, guys? Any questions? Sorry?
I just want to say thank you for your presentation. This is Abdullah from the United States.
Oh,
thank you.
I thought there were only 4 people. You have any other questions, Abdullah, by any chance?
No, thank you.
Okay.